Welcome to this lecture on predicate logic. Till now, we have talked about what is predicate logic, how do we define predicates, how do we specify predicates, and we have talked about the two quantifiers, one being the universal quantifier, which stands for all, and the second being the existential quantifier, which stands for there exists. We have seen how to use these two quantifiers. We have seen how these two quantifiers can be used to specify the informal statements into formal statements. Say, for example, a statement like all students are intelligent. If let us say I have a statement like all students are intelligent, then I can specify this. First of all, what I'll do is I'll define two predicates. Let us define first predicate Px. X is a student, and I'll define another predicate, let us say Qx, which says X is intelligent. Then if I say all students are intelligent, all indicates the use of universal quantifier. So I'll specify for all X, P of X implies Q of X. What it means is for all values of X, here the universe of discourse will be all the students. For all X, if X is a student, then X is intelligent. Say, suppose I have a statement like some students wear uniform. Once again, I'll define two predicates. Let us say Px specifies X is a student, and let us say Qx specifies X wears uniform. Now here the use of the word some indicates that I'll be using the existential quantifier over here. So I'll specify there exists a value of X such that X is a student and X is wearing the uniform. So this is how we specify the for informal statement to formal statement. In this lecture, we are going to talk about the bound variables, free variables, and how to use multiple quantifiers or how to use the nested quantifiers. So let's begin. Let's first understand what are free and bound variables. Say for example, I have a statement like Px. This is a predicate that is defined on the propositional variable x. Now this is called this is said to have a free variable x, as the value of x does not have any boundation on it. If I simply write p of x, then x here is a free variable. Suppose I have another, let us say, predicate which says q of x comma y, then both x and y are said to be free variables, in the sense that neither the value of x nor the value of y has any boundation on it. But if I specify a quantifier over it, say for example for all x, now what I have done is I have put on a condition on the value of it. I have put on a bound on the value x. Now x is bounded by this quantifier for all, or suppose if I specify there exists. Now once again x has been bounded by this quantifier. This says there exists a value x. Now when I use a quantifier, then the variable no longer remains a free variable, but it is now called a bound variable. So in a nutshell, if a variable does not have a quantifier assigned to it, then it is said to be a free variable, and if the variable has a quantifier assigned to it, then it is called a bound variable. Say for example, if I specify there exists, for all x, q of x comma y. Now here there are two variables x and y, but there is only one quantifier which is defined on the value x. So x here will be the bound variable and y here will be the free variable. Suppose I say there exists y, q of x comma y. Now here x will be the free variable and y will be the bound variable. If I specify, let us say for all x, for all y, q of x comma y, here x and y both will be bound variables. So in a nutshell, Any variable for which a quantifier has been defined is called a bound variable, and the variable for which no quantifier has been defined is called a free variable. Now, the quantifiers, they have higher precedence than all logical operators. This is a very important point. Say I specify a statement like this: for all x, px and qx. Now, as the quantifier has a higher precedence as compared to the logical operator, which in this case is the conjunction, so this essentially means that this quantifier is being applied only on px. So this actually is for all x, px and qx. Here this x is a bound variable and this x is a free variable. Whereas in this case, I have applied for all x, but I have enclosed px and qx within parenthesis. Now this for all is being applied on both px and qx. That means now both these x's are bound variables. So obviously, if I want to operate against or operate not in accordance with the precedence of quantifiers, then I have to use parenthesis. Right? This is just like your mathematical operations. So let's see certain examples of binding. Pxy has two free variables x and y. You see there is no quantifier that has been assigned over here. So it has two free variables. The one free variable is x and one free variable is y. For all x, pxy has one free variable and one bound variable. Can you identify which is free variable and which is bound variable? Right? Can you identify? Yes, you are right. The free variable is y and the bound variable is x. Why is it so? Because x has a quantifier assigned to it. So as x has a quantifier assigned to it, so this becomes the bound variable, and y does not have any quantifier, so this becomes a free variable. Now another important point, if I specify it like this, p of x where x is equal to 3. Now I have not specified any quantifier, but I have put a boundation on the value of x. So even though I have not used any quantifier over here, but still the x is now a bound variable. Any expression which does not have any free variables is called a proposition. Now see over here, if I specify, let us say for all x, p of x, right? So this is now an actual proposition. Whereas if it has one or more free variables, it will be a predicate. Why is it a predicate? Because there is no boundation on the value of y. Y is still a free variable. So any statement which has all the variables bound is a actual proposition. Why? Because when I specify for all x px, say let's take a simple example. If I specify, let us say px. Now px can have a truth value of true or false depending upon the value x. If I simply specify px, if I say, let us say px says, let's take an example, px says x is let us say positive. Now if I ask you what is the truth value of px, it is not feasible to say what is the truth value of px. It can be positive, it can be negative, x can be positive or negative. So px can be both true or false. So this is a predicate because this variable is a free variable. But now if I bound it, if I bind it, now what does it mean? It means for all values of x, px is true. What does it mean? If I say for all x, px. Now what does it mean? It means for all values of x, px is true. So now this is no longer a predicate. As I say, for all values of x, px is true. That means it has now a specific truth value. So it is no longer a predicate, but it has now become a proposition. The quantifiers can be mixed also. I can combine, I can mix universal and existential quantifiers. Let's see this example. If I have a predicate which uses two variables x and y, I can have two quantifiers. the x can be bound by a universal quantifier or y can be bound by a existential quantifier, right? But please be careful. If you are mixing quantifiers, it is always read from left to right. The order of the predicates is very important. For all x, there exists y. Pxy is not equivalent to there exists y for all x. So ordering is very important. As we'll see in subsequent slides, I'll take certain examples to show you how the ordering is important. But we can mix quantifiers, right? Let's see further. Nested quantifiers. They can exist. A particular quantifier can exist within the scope of other quantifiers. Let's take an example. Let us say the universe of discourse of x and y, these are the two variables, be the set of people, right? And we define a predicate as pxy is x likes y. Pxy is x likes y. This is again up to this point, this is a free variable and this is a free variable, a predicate with two free variables. Now if I specify there exists y pxy, what does it mean? It means I have bound the variable y. That means there exists one particular value of y. Remember, pxy defines x likes y. And on y, I have put on a quantifier there exists. So what it means? There is someone whom a particular x likes. There is someone. That means there exists a value of y which is related to x by the predicate p. That means there is someone whom a particular x likes. So now this y is now a bound variable and x is a free variable. Similarly, for all x within brackets there exists y pxy. Now what it means is everyone has someone whom they like. So for every x, for every person, there exists another person whom they like. So for every person x, there exists a person y such that x likes y. So everyone has someone whom they like. This particular is no longer a predicate, it is now a proposition because there are no free variables over here. X is bound by this and y is bound by this. So it has no free variables. I hope it is clear now. Now, as I said, ordering of quantifier is very important. Let's see an example. If let us say Pxy says x relies upon y. X relies upon y. Now, we have four examples. First one says, for all x, there exists y such that Pxy. Now, what this actually means in simple plain English is, everyone has someone to rely on. What it means is, for every person x, there exists a person y such that x relies on y. So everyone has someone on whom they can rely. Similarly, there exists y for all x pxy. You see these two. X is still bound by a universal quantifier, y is still bound by an existential quantifier, but the order has now been reversed. Now what does it mean? There exists a person y for every person x. That means there must be someone, there exists a particular person y who is related to every value of x. So what it means is, there is someone whom everyone relies upon. That means there is some person y which is relied upon by every value of x. Similarly, if I write there exists x for every y pxy. Now what does it mean? there must exist a value of x which is related to all the values of y. That means there must be a person x who relies on everybody. There must be a person x, there is some person who relies upon everybody. Now if I reverse the order, there exists y, sorry, for all y there exists x. Now it becomes there exists, sorry, a value, a person x, there exists a person x which who is related to all the values of y. That means everyone has someone who relies upon them. Everyone has someone who is relying upon them. That means this particular x, some particular value of x, there must be some value of x which is related to each and every value of y. So everyone has someone who relies upon them. Now, if I have for all x, for all y, it simply means everyone relies upon everybody. Everyone relies on everybody, right? All the values of x, all the values of y are related to each other. So ordering is very important. As you have seen, write the following proposition symbolically where universe of discourse is the set of real numbers. Right? Let's see this example. Write the following proposition symbolically where the universe of discourse is the set of real numbers. For each integer x, there exists an integer y such that x plus y is equal to 3. For each integer, for each means for all, there exist means existential. So I'll have for all x, there exists y such that x plus y is equal to 3. There exists an integer x such that x plus y is equal to x for every integer y. So there exists x for every y, x plus y is equal to x. For all integers x and y, for all x and for all y. There are integers, means there are integers. There exist x, there exist y. There exist x, there exist y such that x plus y is equal to 10. Right? Please understand, while converting a statement from informal to formal, do not stop for checking whether the statement that you are coming up with is factually true or false. What we are doing over here is we are literally converting an informal statement into a formal statement. Now the truth value of that statement can be true or false, does not make any difference. Rewrite each of the following in words where universe of discourse is the set of integers. Now this is an exact opposite question. Here we were doing informal to formal and here we are doing formal to informal. It says for all x, x square is greater than equal to 0. So what this means is for each and every integer x square is greater than equal to 0. The square of every integer is non-negative. Greater than equal to 0 means non-negative. For all x, for all y, x plus y is equal to y plus x. So I can say for all integers, x plus y is equal to y plus x. You remember what is this? This law is called the commutative law. So for all integers, commutative law is true. There exists a value x, there exists a value y such that x plus y is 10. See, this is the same question over here. So there are integers x and y such that x plus y is equal to 10. There exists x for all y, y minus x is equal to y. That means there is an integer x such that this is true for all the values of y. Right? This is similar to your this question. There exists an integer x such that x plus y is equal to x for every integer y. Here we have used x plus y. Here it is y minus x is equal to y. So there exists an integer x such that y minus x is equal to y for all the values of y. Let's see an example, couple of examples from the number theory. It says a number x is even if and only if it is equal to 2 times some other number. Now what does it say? For all x, a number is even if and only if there exists another number y such that x is twice y. See, you have to read it very carefully. What does it say? X is even, which is defined by this predicate ex. If and only if, remember this is the biconditional. If it is equal to 2 times some other number, right? Some other number, let us say y. So it says for all values of x, the ex is true. What is ex? X is even. Ex is true if and only if and only if there exists a value y such that x is equal to 2y. There, for every value x, e of x will be true if or only if there exists another number y such that x is equal to 2y. Right? This is set of natural numbers. Let's take a simple example. Let us say x is equal to, let us say 4. E of x is true if and only if you can find a value of y as, let us say, 2 such that x is equal to twice of y. If let us say x is equal to 3, can you find a value y such that x is equal to 2y? No. So this is false. A number is prime defined by the predicate px. IFF means if and only if, which is biconditional. If it is not the product of two non-unity numbers, what it means is a number is prime if it is a product of, let us say, if it is a product of two numbers, then one of them must be 1. It cannot be possible that there are two numbers, both of them are not equal to 1 and their product is equal to this given number. So for all x, p of x, that is x is prime if and only if there does not exist, see, this is the negation, there do not exist values y and z such that x is equal to yz and y is not equal to 1 and z is not equal to 1. So what it means is, let me repeat it once again. It says for all the values of x, x will be prime if and only if there does not exist two values y and z, both of them not equal to 1 such that x is equal to yz, which means if x is a product of two numbers, at least one of them must be equal to 1 if x is to be a prime number. Right? I hope it's clear. Now we come to an important point, negating of quantifiers. The negation of quantifier. The rule for negation of quantifier are quite simple. The universal quantifier is negated to be a existential quantifier and vice versa. The negation of for all x px is there exists x such that px is false. And the negation of there exists px, there exists x such that px is true is for all x negation of px. See, what it actually means is, if I say px is true for all the values of x. Now how do I negate it? If I find a single value for which px is not true. So there exists a value x for which px is not true. If I say Px is true for some values, how do I negate it? If I can show that Px is not true for any of the values, or in other words, for all the values Px is false. So this is how you negate. So let us negate. For all x, x cube is equal to x will be simply written as there exists x such that x cube is not equal to x. If I write there exists x such that absolute value of x is equal to x, so I'll write for all x, absolute value of x is not equal to x. So the negation of universal is existential and the negation of existential is universal. Let's see some more examples. This we are finishing off the topic. This is the last thing. Let's see some examples. We'll negate the following. We see for all x in real numbers, x is greater than 3 implies x square is greater than 9. We have to negate it. For all x belonging to the set of real number, x greater than 3 implies x square is greater than 9. So the negation will be, so this is simply, you can write it as for all x, you can understand it as, let us say px implies qx, right? Remember when I talked about the implication, we said that negating the implication is directly not possible. So what we do is I can write it as negation of px or qx. So this is what I'm doing over here, negation of px or qx. So I have to negate this entire thing. Let's apply the De Morgan's theorem over here. So I get negation of, see, if I have to negate this entire thing, so this becomes negation px and negation of qx, and this by involution law becomes px and negation qx. This is exactly what I'm doing over here. There exists, see, this universal will become existential. So px and negation of qx. See, qx was x square is greater than 9 and negation of qx is x square is not greater than 9. There exists y for all x, for all z, px, y, z. So existential gets converted to universal. Universal gets converted to existential and this predicate is negated. Universal existential and implies existential universal, and going by the same logic as here, pxy and negation of qxy, going by the same logic over here. Existential universal, and here I have or, see, I have px or qx. So if I apply a negation over here, so what I'll do is I'll apply the De Morgan's theorem, so it will become negation of px and negation of qx, and this existential will become universal, universal will become existential. So negation px and negation qx. Existential, x plus 6 is equal to 25. So universal, x plus 6 is not equal to 25. Universal, x is less than 25. This will become existential, x is not equal to 25. Right? So now we have seen how to use multiple quantifiers. We have seen how to nest the quantifiers. We have seen how to negate the quantifiers. Please remember, order of the quantifiers in a statement which is using multiple quantifiers is very important. In the next lecture, we will see quantified rules of inferences. Till then,